Okay, so we'll start today's class. Just quickly, I'll go through the conditions of interference and because we need. Hello,
मैम वॉइस डिस्टॉर्ट हुआ थोड़ा सा अभी.
can you hear it now?
यस मैम.
Okay, so I'll just okay, so if you remember that the conditions of viewing, so we were doing interference and we started with interference by division of wavefront. And if you remember that the conditions of viewing sustained interference in any kind of interference setup are first that the sources must be coherent. We can view a interference fringe pattern only if the light is coming from coherent sources. The distance between the screen and the slits, that is the sources, must be fairly different. D must be much greater than the distance between the sources. The sources themselves, that is the virtually coherent sources, must be equidistant from the main source, the original source, and the source must be monochromatic so that we can see the fringes distinctly, otherwise there will be overlapping of the different wavelengths. And this is very important because we are going to need this in today's class, that for getting highly contrasting fringes, the intensities of the interfering rays must be equal or nearly equal. All right. And of course, the sources must be in the same state of polarization. All right. So we then calculated the fringe width for Young's double slit setup, and we had obtained the fringe width to be finally, okay, these we had done. So the final fringe width was found to be lambda capital D by D. So we discussed that the fringe width does not depend on anything other than the constants of the experimental setup, that is the wavelength of the monochromatic light, distance between the screen and the sources, and the distance between the two virtually coherent sources. And of course, these are fringes of equal thickness. All fringes are equally thick, the dark fringes, the bright fringes, independent of the order. If you are viewing near the central fringe or you are viewing very away from the central fringe, they are all of equal thickness. This is very important. Okay. And then we saw what the orientation of the fringes were. If you have vertical slits, you have vertical fringes. If you have horizontal slits, you have horizontal fringes. The shape of fringes, what we see are straight lines, but what the actual shape of the fringes are rectangular hyperbolae, and we see only the straight line portion of the rectangular hyperbolae because that is possible, that is only thing that is possible in the laboratory, in the limited distance of the laboratory, and this is the mathematical expression for the shape of fringes. And then we discussed about redistribution of energy, that is where does the energy go that is absent in the region of dark fringes. We said that there is no destruction of energy. Energy of disappearing at the positions of dark fringes simply reappear at the position of bright fringes. So there is redistribution of energy. Okay. Then we discussed about the displacement of fringes. If you place a transparent material in front of one of the sources, the fringes get displaced, and we calculated this displacement. And we also studied the fact that this method is a method of optically measuring the thickness of very thin transparent materials, which cannot be mechanically done using a screw gauge or a spherometer or a slide caliper, because that would break the material, the sample. So this is a very, very important method of optical measurement. And after this, we studied another experiment which also separates the wavefront coming from a single source. But here, unlike in Young's double slit experiment, it is done by the method of reflection. So this is Lloyd's single mirror. We have this mirror. This also I explained in the last class. So the red rays are the ones getting reflected from the mirror, and the blue rays that are going directly to the screen. So if you extrapolate the red rays, you can go back to a virtual source which are sort of producing a diverging wavefront, and this red wavefront interferes with the blue wavefront, producing a fringe pattern similar to that of Young's double slit experiment. Only here we have one real source and the other virtual source, but of course the sources are still coherent. Okay, and the one thing that we said, that there is a reflection backed by a denser medium which introduces a phase change of pi, and this we will discuss in today's class. Okay, and then we gave the mathematical expressions for a condition of bright fringe and dark fringe, and we saw again that the fringe width in this case 2 is lambda capital D by D, same as Young's double slit. The only difference is that the position of dark and bright fringes are interchanged, and in Young's double slit the fringes appear symmetrically about the central bright fringe, whereas here they appear only on one side of the 0th bright fringe. Okay, now the next experiment that we are going to study, that again uses division of wavefront, is Fresnel's biprism, and this is a tad bit more important for you because you have this experiment in your practical syllabus. All right, we have this set up in our laboratory when and if, I'm sure we will get back to college in maybe in July, we will get to do this in the laboratory. So let us first see what a biprism is. All right. So you have all seen a monoprism. Did you have an experiment using a prism in your first sem? Did you have any optics experiment in your first sem?
No, ma'am. No, ma'am.
But have you all seen a prism?
Yes, yes.
You've seen a prism. So you know that a prism is kind of, this is of course a horizontal cross section. It's pyramidal in shape, and this is a monoprism, right? If you slice a monoprism vertical section, then this is what you get. Now a biprism is basically two prisms, not monoprisms, okay? Two prisms that are attached together. They are actually two prisms of same material, and it is called, although it is called a biprism, but actually it is developed from a single glass, but its shape is such that it acts as a biprism. Okay, the glass is cut such that these two angles are each 30 degree, and the peak angle in a monoprism, we know that angle A is usually 60 degrees. You've all studied it in your high school optics. In a biprism, the peak angle, this is about 179 degrees. Okay, so this is a biprism. Now let's see what happens in an ordinary monoprism that we use in the laboratory. You all have done this diagram for several times, I think starting right from your secondary level, class 9 or 10, I think. So what does an ordinary prism do? Light coming from a source gets deviated inside the prism, and then when it comes outside, it again enters the rarer medium, and so it is further deviated. And if you take this ray backwards, you will see that it sort of comes from a virtual source S prime. Okay, and this is the angle of deviation. This is what a monoprism, a single ordinary prism, does, and we use it for separating the different colors of light, because as it deviates the different colors by different angles on the if the incident ray is white, then on the emergent side we get the different colors. Now in a biprism, a spectrum is not produced, neither do we want to use it to produce a spectrum. We use it simply to separate wavefronts. Now how is this wavefront separated? Okay, so what happens in a biprism? As you can see now that we have two triangles attached in the middle at the bases of the two triangles. So what happens is, if you have a single source placed symmetrically about the two triangles, then the top triangle will deviate it towards the sort of downwards, and the bottom triangle will deviate it upwards. So if you extrapolate these two deviated rays, they appear to come from two separate sources, S1 and S2. All right. So two prisms A and B deviate the two rays from a single real source S, and they appear to come from two virtual sources S1 and S2. And since these rays actually originate from the single source S, so the virtual sources are therefore coherent. Okay, so this is the principle that is used in biprism, where you separate the wavefront, produce two coherent sources from one single source. All right. So the experimental setup now. It looks a little bit cumbersome. You've never used such a setup before, but once you read through and then you go and use it in the laboratory, it doesn't become as difficult as it looks like. So this thing is called an optical bench. It's like a rail. There are two rails, and on the two rails, this long thing, you can move these stands horizontally, okay, so that you can change the distance between the source and the lens and the prism, etc. Okay, so this entire setup is called an optical bench. Okay, this is the mounted prism. This transparent portion is the prism. Okay, it is mounted on a stand so that it can be moved horizontally on the optical bench, and the different distances can be adjusted to see the fringes. All right, this is a single source, and of course you cannot see the two sources, but once you place the prism using the eyepiece, you can actually see the two separate sources, and then you can see the fringes that will appear on the eyepiece. We use the micrometer eyepiece because we need to measure the positions of the fringes. You can do it on a, this could be done on a screen too, but since we need to measure the positions of the fringes, we use the eyepiece. All right. So this is theoretically what is happening. Single source. So the refracting edge of the prism, this is the refracting edge. Where is my cursor now? Okay, it's kept parallel to the slit, and a single wavefront is incident on both the prisms coming from the single source S. Then the upper prism, this portion, deviates the upper part of the wavefront, and then so you get it on the screen as this thing OR, and when you extrapolate this, it appears to come from a source S1, virtual source S1. And the lower prism, this lower prism, it deviates the ray in the opposite direction, and they appear on the screen at the position M. This should have a name over here, MO prime, say. And if you extrapolate them, then they appear to come from a virtual source S2. So S1 and S2 of course are coherent, and the wavefront splits up, and they appear to emerge from two different coherent sources. So they interfere, producing fringes on a screen placed at a suitable position on the right hand side of the prism. And as I told you, in the laboratory, the fringes are observed using a micrometer eyepiece. So using the value of small d, the distance between the virtual sources, and capital D, the distance between the screen and the source plane, we can measure the fringe width as beta equals to lambda capital D by small d. Once again, same as, because you can see that the treatment or the analysis would be same as Young's double slit experiment, because it's exactly the same. Two sources producing two wavefronts which interfere on the screen. So fringe width is lambda capital D by D, and this is your fringe pattern that you observe on the screen. So you, with this background now, when you go and do your biprism experiment in the laboratory, I think it will help you. Nothing much more to study in this, only the qualitative study. You can get problems using this fringe width formula and parameters given. All right, there is no mathematical analysis, separate mathematical analysis required to do in biprism, Fresnel's biprism. You need to know the diagram and you need to know this working, how the two coherent sources are produced, why this is used for wavefront division, and you need to know the formula of the fringe width. All right. So that finishes the first part of our interference module, that is interference by division of wavefront. So we did principle of superposition. We got a relation between intensity and amplitude, and finally we could analyze how, when a single wavefront is divided into two wavefronts by Huygens principles, how they interfere and what the mathematical expression of the fringes, the fringe width would be, what are the conditions of maximum and minimum, etc. All right. So now we will move on to the next part of the syllabus. Okay, are you all with me? Since I cannot see your faces, I need to verify this from time to time. সবাই শুনতে পাচ্ছে?
Yes, ma'am.
Okay.
Yes,
Yes,
ma'am.
ma'am.
Okay. Okay, so let's start the next part of the syllabus. Okay, now in this next part, there will be things that are completely new and are very, very important concepts. So I will go a bit slowly, and since in class what happens is I can see your faces and I can understand when your saturation level is reached so that I can stop. Here I cannot see your faces, so I can go on, and it can be that you cannot understand anything that I'm saying. So I would like you to please stop me when you see that you cannot take any more. All right, I'll ask you, of course, at the ends of modules, but you need to understand till what, if I teach in this particular session, it will be easy for you to, go back through the notes and understand, and then move on to the next part. All right. Okay, so what we'll do is today, interference by division of amplitude. As we discussed in the first class, that interference can happen in two ways. The first way we studied, that is division of wavefront, where two virtual sources are produced, or one real source and one virtual source, and the two wavefronts then interfere, producing fringes. The other way in which interference can be possible is interference by division of amplitude. Okay. So before we actually start studying interference by division of amplitude, we need to know certain definitions. And the first definition is that of optical path. All right. So what is optical path? Okay. So this is a bit similar to the problem of Young's double slit experiment that we studied, where we placed a transparent material in front of one of the slits. All right. So what we have over here is two sources placed at A and C, and two observers placed at B and D respectively. So AB and CD have the same length L. AB equal to CD equal to L. Okay, geometrical distance is same. Now what we do is, a very thin slab of a transparent material having refractive index mu and thickness t, t of course is very small, is placed in the path of the ray AB. So we keep this slab in front of the source A. All right. Now, the time taken for light to reach the point D, that is the observer at D, from the source C is given by this tau CD equal to distance by speed. Speed of light is c, distance traveled is l, so tau CD equal to l by c. What is the time taken for light to reach B from the source A with this transparent thing kept in its path? It's given by time taken by light to travel in air and time taken by light to travel in the material. Okay, so it is traveling a distance capital L minus T, the thickness of the slab in air, and this distance it travels with a speed c, speed of light in air, so it's given by L minus T by c. Whereas within the material, it is traveling with a speed c mu, its speed in the material of refractive index mu. So time is t by mu. Okay, don't confuse yourself with this symbol. This symbol small t is of thickness and not time. Tau is the symbol for time over here, right? Where you can write c mu, the speed of light in the material of refractive index mu, as c by mu. You all know this, mu equal to c by c mu. So c mu equal to c by mu. So this, if you do a little bit of algebra, tau AB, the time taken by light to reach B from A, is this L plus T into mu minus 1 by C. Okay, and you can clearly see that tau AB is greater than tau CD. That is, when you keep a material of a different refractive index in the path of light, then light takes more time to travel than when it travels in air or vacuum. You all know this conceptually. Here I have shown mathematically that the time taken by light to travel in the first case is greater than the time taken by light to travel in the second case. So let's now look at this expression tau AB over here. Clearly you can see that the distance traversed in air is L minus T, and the distance traversed in the material is given by mu T, right? If you take this expression, then this is basically distance divided by speed, and you can see that the distance traveled in air is L minus T, whereas the distance traveled in the material is not T but mu T. Okay, so geometrical distance traversed by light in the medium of refractive index mu is given by T, that's the geometrical length of the slab. However, actual distance traversed by light in the medium of refractive index mu is given by mu T. So this is what we define as optical path. So when light is traveling in a medium of a certain refractive index greater than 1, the actual path traveled by light is defined as the optical path, and it is mathematically given by the product of the geometrical distance and the refractive index of the material. Is this clear to everybody? Because we are going to require this in our future calculations. So is the concept of optical path clear to everybody?
Yes, ma'am.
Okay. Please go through this calculation once this class is over, and try to understand clearly what I said by reading through the material. Now, why have we not come across this before? We have never come across the concept of optical path before, because in air mu is 1, we have till now done most of our optical experiments in air where diffractive index is 1. So when refractive index is 1, clearly optical path is equal to geometrical path. So we did not require to mention optical path separately when we were doing experiments in air, because in air mu is 1 and the two have the same value. But the moment we do our experiment in a different medium, then when we calculate the path traveled by light, instead of the geometrical length, we have to take into consideration the optical path. All right, so that's the first definition. Next is the principle of reversibility of light. Okay, once again, this is a very known concept. You all probably know what I'm going to say, but only you probably do not know the formal language, that is the principle of reversibility of light. Okay, what does it say formally? This is the textbook definition. A wave motion is a strictly reversible phenomenon provided there is no dissipation of energy by absorption. Okay, what does it mean in plain language? A ray of light will retrace its original path if the direction is reversed, provided of course there is no energy absorption anywhere. If you do not keep any absorbing material anywhere that might absorb the light, like a black hole or something, then the ray of light will always retrace its original path. A simple cartoon to show what I'm trying to say is that, suppose this is the source S and this is the observer. If you just interchange the position of the source and the observer, what you simply need to do is change the direction of the arrow. Light will retrace the path. Okay, this is very simple but very important, because it's basically energy conservation, but it's very important in the things that we are going to study after this. All right, things we are going to discuss. Principle of reversibility of light. So you have two not new concepts, but probably placed in a different way, but two very, very important concepts. One is the concept of optical path and the other is the principle of reversibility of light. Now next what we need to do is Stokes' law. Before moving on to analyze the division of amplitude way of interference, we need to know a very, very important law which is known as Stokes' law, and because Stokes' law will give us some information that we will require to utilize when we actually analyze the division of amplitude way of interference. All right, okay. Now we are going to go through a series of definitions and pictures in order to realize what Stokes' law is going to tell us. Now, when a ray of light is incident at the interface between two media, we define two parameters. All right. We know that light is always hitting interface between two material, right? Either it is traveling in air or it is traveling within a material, but it is always hitting the surface of the material or the interface between air and some other material. So when it is doing so, we define two very important parameters. One is small r. What is small r? It is the reflection coefficient. What is reflection coefficient? It gives you the fraction of the incident intensity that is reflected into the same medium. Okay, when light hits a medium, will all of it be reflected or will all of it be transmitted? It is decided by this factor r, the reflection coefficient, how much of the incident intensity will be reflected back. And the other parameter is small t. It's the transmission coefficient. So the fraction of the incident intensity that is transmitted into the other medium is given by the transmission coefficient. So now when you know the value of r and t, you know whether a particular material will be transparent or opaque, right? You know that a material is opaque because most of the light that is incident on it gets reflected and come towards our eye and we see it. And when the light goes through the material, it is transparent and we get to see the things that are on the other side of the material, because light is sort of stopped by the material which reflects the light back to our eyes. So whether a material is transparent or opaque, if its reflection coefficient is very high, it means most of the light will be reflected back and it is opaque. If its transmission coefficient is very high, then most of the light will be transmitted and it is transparent. So is this concept clear to everybody? Have you understood what I'm trying to say? These two definitions are extremely important. These are not done in high school, but although you do reflection and transmission and why objects are opaque and transparent, but this is the factor that decides whether a particular material will be opaque or transparent. And so when we are analyzing light traveling from medium 1 to medium 2, we define the reflection coefficient in medium 1 as R1 and the transmission coefficient for traveling from 1 to 2 as T1. Again, the reflection coefficient in medium 2 as R2 and the transmission coefficient for traveling from medium 2 and back to 1 is T2. So this is how we define. So as you can understand, small r and small t are dependent on the medium, and the transmission is also dependent on the direction of motion of light. If it travels from 1 to 2, you will get one value of t. If it travels from 2 to 1, you will get another value of t. Clear? Okay. So now what we have is, we have a light ray of amplitude A incident at the interface of media 1 and 2. 1 is the rarer medium and 2 is the denser medium. So clearly, if this is the incident ray of amplitude A, some part of it will be reflected and some part will be transmitted. What part will be reflected? R1. So the amplitude of the reflected wave will be A into R1. R1 fraction of A, so AR1. Amplitude of the transmitted ray will be AT1. T1 fraction of A, so AT1. Is this clear to everybody? Because this is very, very important. If you've understood this, only then I can go to the next step. Do you want me to repeat this once more, or is it clear to everybody? Hello? Hello?
Yes, ma'am.
Have you all got me? Because very, very important concept. I need it to be sort of crystal clear in your heads what reflection coefficient, transmission coefficient are, why we are taking these amplitudes to be AR1 and AT1. Is it clear to everybody? Can I carry
Yes,
on?
ma'am.
Okay.
Yes, ma'am.
So,
Yes, ma'am.
sorry. So this is step 1. Okay. So just once again, this is our incident ray. This is the reflected ray of amplitude AR1 and this is the transmitted ray of amplitude AT1. Now we consider another scenario where the source is kept here so that this is our incident ray. So now we have a second scene, same set of media 1 and 2, but now the incident ray has amplitude AR1. Okay. So again, incident ray will be partly reflected and partly transmitted. What will be the reflected ray? Of amplitude AR1 multiplied by R1, same media, so AR1 square. And what will be the transmitted ray? T1 fraction of AR1, so AR1 T1. So now the reflected ray has amplitude AR1 square and the transmitted ray has amplitude AR1 T1. Clear? Okay. Step 3. In the next step, we imagine now the source to be placed here. Okay, so we are dealing with the same 3 rays and the same pair of media, only we are changing the position of the source. Okay, so in our third step, the source is at this point. So now our new incident ray is of amplitude AT1. Again, part of it will be reflected into medium 2 and part of it will be transmitted into medium 1. What part of it will be reflected to medium 2? Now decided by reflection coefficient 2, because now reflection is taking place in medium 2. Original amplitude AT1, so R2 fraction of AT1 will be reflected. So new amplitude of reflected ray is AR2 T1. Transmitted into medium 1. So now transmission is taking place from 2 to 1. So T2 will be the new transmission coefficient. T2 fraction of the incident ray will be transmitted. So T2 fraction of AT1. So the new transmitted ray is of amplitude AT1 T2. Okay. So just once again, we have our first step, simple optical ray diagram. We have done this several times from the time we have studied reflection and refraction. Only now at high sort of undergraduate level, I am calling transmission, not refraction. It is transmitted into the second medium. So incident ray, part of it reflected, part of it transmitted. What part of it reflected? R1. What part of it transmitted? T1. Next, we place the source at the position of the reflected ray. So this is my new incident ray. Again, reflected, transmitted. And according to the definition of transmission and reflection coefficients, we have the new amplitudes of the reflected and transmitted rays. Third step, now source kept at the position of the transmitted ray. So this is my new transmitted ray, incident ray. Again, it is reflected, transmitted according to the new parameters T2 and R2. We have the amplitudes of the reflected and transmitted ray. Now comes the complicated part. Okay, step 4. We still have the same pair of medium 1 and 2 and the interface. First, we have the incident ray as AR1. So this case here, incident ray AR1, which produces the reflected and transmitted rays of amplitudes AR1 square and AR1 T1. Next, I have the incident ray AT1. So it again by itself produces the reflected and transmitted rays of amplitudes AR2T1 and AT1T2. All right. So now I have these two pictures simultaneously over here. So here I had only one incident ray. Here I had only one incident ray. In this step 4, I have two incident rays simultaneously. So we have first incident ray of amplitude AR1, second incident ray of amplitude AT1, and they produce one ray of total intensity AT1 T2 plus AR1 square and another ray of total intensity AR1 T1 and AR2 T1. Clear to everybody? If you want, I can explain this fourth picture once more. Do you want me to explain the fourth picture once more, or I can carry on?
Yes. Ma'am,
You
please
want me to explain
repeat.
it once more?
Yes, ma'am.
আর একবার বলবো?
Yes, ma'am.
Okay. Okay, let's go back. এতক্ষণ কি ছিল? We had single incident rays. This is the first case, this is the second case, this is the third case. In the fourth case, I first have this as my incident ray, which produces the reflected and transmitted rays AR1 squared and AR1 T1. Simple. We also have another incident ray. It is possible to make two rays incident at the same time, right? If you place two sources, one over here and the other over here, then we have two sources sending incident rays simultaneously. So we have one incident ray of amplitude AR1 and second incident ray of amplitude AT1, you have to understand that these two rays are incident at the same time. They are coming in simultaneously. Okay? So when they are coming in simultaneously, what do we get? We get one ray in medium 1 of total intensity AR1 square due to this and AT1 T2 due to this. All right. And a second ray in medium 2 with total intensity AR1 T1 due to this and AR2 T1 due to this. Clear? Okay.
Yes, ma'am.
Okay, so now I will draw these pictures once again. Step 1, understood. Single ray of amplitude A divided into reflected and transmitted rays of amplitudes AR1 and AT1. Step 2, single ray of amplitude AR1, therefore divided into rays of amplitudes AR1 squared and AR1 T1. Step 3, single ray of amplitude AT1 divided into reflected and transmitted rays of amplitudes AT1 T2 and AR2 T1. And finally, two rays of amplitudes AR1 and AT1 incident simultaneously, therefore producing two rays, one in medium 1 of total amplitude AR1 square plus AT1 T2 and another ray in medium 2 producing total intensity of AR2 T1 and AR1 T1. All right. So these are the 4 steps. Why do we need this? What comes out of this? If we want to maintain the principle of reversibility of light that we studied before this, this should be the scenario. See, if the source is here and these are the two rays, then if you simply keep the sources at this point and this point, then the simply the directions of the rays will be changed, and therefore the direction of this ray reverses, and this scene should change to this scene if you want to maintain the principle of reversibility. If the original picture is this, then simply reversing the directions of this ray and this ray should produce this picture if you are to believe in the principle of reversibility of light. So, applying the principle of reversibility, you should have the total amplitude of this ray over here, AT1 T2 plus AR1 square, equal to the amplitude of this ray here. All right. That is, this gives T1 T2 equal to minus R1 square. And the total amplitude of this ray AR1 T1, AR2 T1 should be 0 because this ray does not exist. In other words, R1 equal to minus R2. Okay? So you might ask, where does this go? Since we are dealing with light, and you know that in the beginning of the lesson I said light added to light need not always produce more light. So must be that in order to maintain the principle of reversibility, they are cancelling each other out, they are enhancing the ray over here. Okay? So when the two rays are incident simultaneously, we see that a single ray of amplitude A is produced. That is to maintain the principle of reversibility, and this exercise gives us the relation between the reflection and transmission coefficient when light travels from one medium to another. We see that the product of the two transmission coefficients is equal to the square of the reflection coefficient with a minus sign, and we see that the reflection coefficients are the same in magnitude, but they only differ in their sign. Okay? Have you all got me? Should I move on, or do you want me to explain this once more? Should I move on? Hello?
Yes, ma'am.
Okay. Now, this is not, you might not, grasp this concept immediately. After the class, when you get the PDF files, please just go through the steps, recall what I said, and then it will be easier for you to understand how we are getting this. Okay? Just remember that the main thing that we are using over here is the principle of reversibility of light. Okay? So we got this relation that the reflection coefficients in the two media have the same magnitude, but they have opposite sign. So the negative sign, what does it indicate? It indicates a phase change of pi. A particular quantity reversing its sign means it has undergone a phase change of 180 degree, that is pi. Now whenever there is a phase change of pi, we have a path difference of lambda by 2 associated with it, and I have just done the algebra for you to recall why lambda by 2. You see the definition of phase difference is 2 pi by lambda into path difference. So path difference is equal to lambda by 2 pi into phase difference. So here phase difference is pi. So path difference is lambda by 2. So we see that when this phase difference, phase change of pi takes place, it has to be associated with a path difference of lambda by 2. So now we are at a position to state the formal statement of Stokes' law. This exercise that we did with the 4 cases of light getting reflected and transmitted in 4 different ways from the same sources and in between the same media was basically to arrive at the formal statement of Stokes' law. What is that? It says that there is a phase change of pi and an additional path difference of lambda by 2 associated whenever there is a reflection backed by a denser medium. Remember, we had taken medium 1 and medium 2, where medium 2 was denser than medium 1. So, whenever there is a reflection backed by a denser medium, there is a phase change of pi and an additional path difference of lambda by 2 associated with it. This is Stokes' law, and we are going to apply this several times when we do the different kinds of interference backed by denser medium. Just we have to remember that this statement, this part of the statement which says reflection backed by a denser medium is experimentally established. If you do the mathematics, any pair of media should give you the same result, but it has been seen that experimentally this happens when light is reflected by a backed by a denser medium. I mentioned this while doing Lloyd single mirror, and I also said this was very important. This is why it is very important, because it gives us the formal statement of Stokes' law. All right. So we went through the concept of optical path. We saw what the principle of reversibility of light is, and using that we came to the formal statement of Stokes' law. So this is the background exercise we require in order to move on to studying interference in thin parallel films. All right. Are you totally saturated? Should you want, or do you want me to carry on? Hello? Hello? Hello?
Yes, ma'am.
Can I go ahead a little more?
ম্যাম একটা কোশ্চেন আছে একটু
বলো।
একবার ওই যে স্লাইডে ওই
কোন
স্লাইডটা
স্লাইড?
একবার ওপেন করুন, এর
কোনটা
প্রিভিয়াস
বলো?
স্লাইডটা, এর আগেরটা।
এই কি হয়ে গেল? এইটা?
না ম্যাম, এর
এরপরেরটা?
পরেরটা,
এরপরেরটা।
এরপর।
বলো।
ম্যাম
বলো।
ওই যে লেখা আছে AR1T1 প্লাস AR2T1 ইজ ইকুয়াল টু
হ্যাঁ,
0,
হ্যাঁ,
ওখানে AT1R2 হবে একটা, AT1R2 যে একটা রে যাচ্ছে, AT1 অ্যাম্পলিটিউড নিয়ে যে রেটা যাচ্ছে সেকেন্ড মিডিয়ামে যেটা আছে,
হ্যাঁ,
AT1R প্লাস AR1T1।
হ্যাঁ। এই যে
তাহলে ম্যাম এখানে লেখা আছে,
AR1T1 আর AR2T1।
হ্যাঁ ম্যাম বলছি AR1T1টা ঠিক আছে,
হ্যাঁ।
আর বলছি AR1T1 আর AT1R2 একই, না ঠিকই আছে, না ম্যাম ঠিকই আছে, একই আছে।
AR1T1টা হচ্ছে এই যে AR1টা ট্রান্সমিটেড হলো, তাহলে কত ট্রান্সমিটেড হবে? T1 ফ্র্যাকশন অফ AR1। আর AR2T1 হচ্ছে এই যে AT1টা রিফ্লেক্টেড হলো, কতখানি রিফ্লেক্টেড হবে? R2 ফ্র্যাকশন অফ AT1, AR2T1। তাহলে এইটার টোটাল অ্যাম্পলিটিউড হচ্ছে AR1T1 প্লাস AR2T1। কিন্তু এই রেটা তো এক্সিস্টই করতে পারে না বিকজ অফ প্রিন্সিপাল অফ রিভার্সিবিলিটি, তাই এদের টোটাল অ্যাম্পলিটিউডটা 0।
ম্যাম
ঠিক
বলছি
আছে?
R1 R22 মানে ফিজিক্যাল মিনিংটা কি, এটা যে অ্যাম্পলিটিউডের ফ্র্যাকশন, যে এই যে
ফিজিক্যাল
AR1,
মিনিং হচ্ছে এগুলো হচ্ছে প্যারামিটারস। এই যে প্রথমেই যখন R1 আর T1 ডিফাইন করলাম, ফিজিক্যাল মিনিং হচ্ছে ধরো একটা লাইট রে এসে, এই যে একদম প্রথমেই যেটা বললাম যে ইট ডিসাইডস how much a body is opaque or how much a medium is opaque, how much a medium is transmitted. যত বেশি ভ্যালু হবে, it is totally medium dependent. So the
ম্যাম
higher the value of R, the reflection coefficient, it means more and more part of the light incident will be reflected back. so it is more opaque. যত বেশি light will be reflected back from a particular medium, that medium will be opaque. আর যত t এর ভ্যালু বেশি হবে তার মানে more fraction of the light will be transmitted into the medium than it is reflected. Incident amplitude টা তো fixed, ওটা তো চেঞ্জ হচ্ছে না।
মানে ম্যাম ওটা অ্যামপ্লিটিউডের উপর কি ডিপেন্ড করে না? যে কোনো অন্য যদি ওয়েভ নিই আমরা, অন্য অ্যামপ্লিটিউড বলা যদি একটা অন্য ওয়েভ নিই, তাহলে কি ওই অ্যামপ্লিটিউডের উপরে R1 বা T1 কি ডিপেন্ড করবে না?
ওটা R1 আর R আর T হচ্ছে অনলি মিডিয়াম ডিপেন্ডেন্ট, অনলি মিডিয়াম ডিপেন্ডেন্ট। যত অ্যামপ্লিটিউডের ওয়েভই তুমি নাও না কেন, তোমার ওই পার্টিকুলার মিডিয়ামটার জন্য আর ফ্র্যাকশনই রিফ্লেক্টেড হবে।
আচ্ছা,
ঠিক আছে?
হ্যাঁ।
হ্যালো,
হ্যাঁ বলো।
ম্যাম বলছি আমি মূল বক্সটাতে T1 T2 ইকুয়াল টু 1 মাইনাস R1 স্কয়ার তো?
হ্যাঁ 1 মাইনাস R1 স্কয়ার হবে, এটা মাইনাস R1 স্কয়ার হয়ে গেছে।
তো আমরা তো একটা কনক্লুশন করতে পারি যে T and T dash are the same sign because R lesser than 1, so no phase change occur between incident and transmitted ray.
Now when it is getting transmitted there is no phase change. The phase change, হ্যাঁ thank you for indicating, আমি এটা এক্ষুনি চেঞ্জ করে নিচ্ছি আমার স্লাইডে। The phase change occurs only when it is reflected back by a denser medium. There is no phase change on transmission. The light does not endure any phase change when it is transmitted. There is phase change only on reflection. Very good, thank you for indicating.
এটা প্রথমটার থেকে তো এইটাই কনক্লুশন আছে, আর সেকেন্ডটার থেকে তো মানে ফাই চেঞ্জের কনক্লুশনটা আসবে।
কেন কনফিউশন কেন? এই যে সাইন চেঞ্জ হয়ে যাচ্ছে মানে পাই,
হ্যাঁ ওইটা মানে পাই চেঞ্জটা হবে, কিন্তু লেলর মিরর অনুযায়ী সেকেন্ডটা কি আমরা তো কনসিডার করব R1 ইকুয়াল টু মাইনাস R2।
হ্যাঁ কিন্তু এখানে তো পুরো স্কোয়ারের সামনে একটা মাইনাস আছে, তাহলে মাইনাস তো থাকলোই।
হ্যাঁ মাইনাস থাকবে।
ঠিক আছে?
হ্যাঁ
হ্যাঁ ঠিক আছে, তাহলে যাই নেক্সট স্লাইডে। আচ্ছা এইটা বোঝা গেল, তাহলে স্টোকস ল হয়ে গেল আর ব্যাকড বাই ডেন্সার মিডিয়াম। আমি এই থিন প্যারালাল ফিল্মের ম্যাথমেটিক্যাল অ্যানালিসিসটা আজকে করব না, শুধু কোয়ালিটেটিভলি থিন প্যারালাল ফিল্মটা কি জিনিস, কি হচ্ছে একটু বলে দিয়ে আজকে ছেড়ে দেবো। ঠিক আছে? মানে অ্যাকচুয়াল ক্যালকুলেশন যেটা সেটা পরের ক্লাসে করব, আজকে একটু কোয়ালিটেটিভ ডিসকাশন করব, সেইটুকু অন্তত করে দিই, কারণ না হলে এই স্টোকস লয়ের আর ইয়ের কনসেপ্টটা আবার চলে যাবে। আচ্ছা, before going on to the analysis I'll show you some pictures. Okay, all of you have seen these things যখন আমরা রাস্তায় বেরোতাম once upon a time 1 month back. So these two, the first and the third pictures are of course oil spilt on wet road, and I'm sure all of you have seen these patterns formed. দেখেছো তো সবাই? দেখেছো? This is a bubble, very beautiful picture taken from the internet, and these bubbles also, when you look at it from different angles, you can see these colors formed on the bubbles. So basically all these beautiful pictures, these are result of a very, very practical interference phenomena, that is interference in thin parallel films. All right. So what is a thin parallel film? This is a thin parallel film. এই যে পিকচারটা simple. We have air, we have a medium of refractive index mu, and then we have air or some other medium also. For simplicity we'll consider that this medium of refractive index mu is flanked by air on both the sides, and it has a thickness small t, and it's a parallel film, so the thickness is same throughout till wherever the film continues, it has the same thickness t. Okay, and t is very small, which is why we call it a thin parallel film. Now something very interesting happens when a single ray of light, of course you cannot single out a ray of light, But even when a single ray of light is incident on such a film, something very interesting happens. What is it? See, I have a single ray of light of a certain amplitude incident, and I have also drawn the normal. So what will happen to it? Part of it will get reflected and part of it will get transmitted. Up to here, we all know. Now see, when the transmitted ray goes and hits the second boundary of this film, of this thin parallel film, again it will be reflected partly and part of it will be transmitted. Right? Now this ray, when hitting the upper boundary, again it will be partly reflected and partly transmitted. And this new ray, which is hitting the lower boundary, will again get partly reflected, partly transmitted. And this will go on, reflection, transmission, reflection, transmission, reflection, transmission, and so on. Okay? So what I want you to, and this will go on, till the film continues. So what I want you to realize is that we had started with a single ray, and from the single ray, due to multiple reflection within the film, we are getting several rays on both sides of the film in air. Okay? We have started with a single ray, remember. But we are getting a series of rays on one side, on the upper side, and a series of rays on the lower side. These are the amplitudes of the different rays once you have the concept of reflection and transmission coefficient. Okay? এগুলো নিজেরা একটু ভালো করে দেখবে amplitude গুলো দেখো incident ray has amplitude A. So first reflected ray AR, first transmitted ray AT. Okay, now this transmitted ray again gets reflected, so new amplitude of this ray ATR and transmitted ray ATT prime. Okay, again this ray gets reflected, so ATR multiplied by R, ATR square, and this transmitted ray ATR into T prime. ATR again gets reflected, so ATR into R, ATR cube, and transmitted ray ATR square into T prime, ATR square T prime, and so on. You can tell me, why have I taken single value of R whereas I have taken T and T prime? Because air on both sides, so transmission between the two media is T prime. Transmission from air to mu is T. Transmission from mu to air is T prime. But since the magnitude of R is same, R1 equal to minus R2, so we do not take into consideration the sign. We take into consideration only the magnitude, because we have to remember that intensity is amplitude squared. So whatever be the sign, when you square it, it will be the magnitude only that will count. Is it clear to everybody? Okay?
Yes,
What
ma'am.
you need to realize is that a single ray of amplitude A is giving rise to so many rays. Obviously, the amplitude will fade out very, very fast. And as you move on, although theoretically there will be many such more rays present, but the amplitudes will be drastically less as you move on to the rays further away from the incident rays. And this is called the reflected mode, because the first ray in this side is reflected. This is called the transmitted mode, because the first ray in this side is transmitted. Okay, now before moving on to the interference part, let's calculate the sum of the amplitudes of all the rays in the reflected mode other than the first one. Okay. So what is the sum of the amplitudes of all the rays in the reflected mode, leaving aside the first one? I've denoted it by A. So you see A T R T prime plus A T R cube T prime plus next will be A T R to the power 5 T prime, etc. So it will be like this, and since r is less than 1, so using binomial expansion, we can write 1 plus r square plus r to the power 4 this series as 1 by 1 minus r square. But from the Stokes' law first part, we saw that 1 minus r square is t prime. So we get the amplitude of all the rays except the first one as ar, which means that the amplitude of all the rays in the reflected mode is equal to the amplitude of the first reflected ray. So you can understand that the first reflected ray is extremely bright, whereas the other reflected rays are of gradually dwindling amplitude. All right. Now, so this is what we had right now. Amplitude of first reflected ray is equal to sum of amplitudes of all the other rays. So the first one is the brightest. Now question is, who does this ray interfere with? Clearly, if you look at this picture, then these are the interfering rays. But we have not studied multiple ray interference. We have studied only two ray interference. So who does this first ray interfere with? Okay, that should be our question. So now we will calculate the amplitudes of individual rays in the reflected mode. Very easy. Second ray amplitude is ATR T prime. Okay, you put the value of T prime, this comes to be AR into 1 minus R square. Since R is much less than A, so you can leave the higher powers, and so this becomes equal to AR. All right. Amplitude of third ray, ATR cube T prime. Again, same reason, this becomes AR cube. Amplitude of fourth ray, in the same way, it comes to be AR to the power 5. And as R is much less than A, and since R is a fraction, you can understand that as you go to higher powers of R, this value will be lower faster than earlier. Okay. So what we have is that the rays have increasingly lesser amplitude. So only the second ray, which has an amplitude AR, is close to that of the first ray in intensity. Okay. So if you remember the criteria for getting interference fringes of good contrast, that is, the intensities must be equal or nearly equal, then you can see from this treatment that only the second reflected ray has amplitude close to that of the first reflected ray. That is, they fulfill the criteria to produce interference fringes of good contrast. So what we are going to do is we are going to analyze the fringe pattern produced due to interference of the first two rays in the reflected mode. Okay. So I think up to this has already become too much. I shouldn't go further. এইটুকু অন্তত conceptually I want you to be very clear about the most of the things that I said today are new concepts. At least I have done this for the first time with you, and I want you to go through this very clearly. In the slides, I have written each and everything very in a very explanatory manner. I have not missed any point. I've written each and everything. Probably even textbooks do not have so many things written. So I want you to go through this and get your concepts regarding this very clear, and in next class we will analyze the thin parallel film interference and do the required calculations. All right. So this is what we are going to study. This picture we are going to analyze and calculate the necessary parameters for doing thin parallel film interference. But I think I should leave that for the next class. I want you to clear your concepts regarding the things, the new things that we did in today's class. Is it all right?
Yes, ma'am.
Okay, so I'll send this PDF and just after I log off, I'll send this PDF file, and before I forget, I want to make this change over here. This should be 1 minus r square. Who reminded this? Thank you very much. Okay, so this is 1 minus r square. All right. Okay, so if you found things all right, go through the slides, and if you have any questions, as I tell you in every class, please get back to me. You can WhatsApp me your questions, you can mail me your questions, and you can also ask me anything regarding the previous class when I come to meet you in the next class. All right, and as usual, one of you please take the responsibility of sending me the attendance of today's class, because I need it for the records. All right then. ঠিক আছে তাহলে আজকের কল কেটে দিচ্ছি।
Yes.
Yes, ma'am.